Hello guys, we finally arrived to the last question of the bi-weekly contest 36. It was a tough question in the sense that firstly you needed to understand the question, and despite this wasn't the most difficult question to understand, this question had a lot of room to confusion and misunderstanding, and I hope to explain to you what is intended from this question in a clear manner, and then I will explain you my solution for this question. Okay. But before that, I just want to say you that I struggled a bit with this question. I implemented, if I'm not mistaken, 3 times, failed at least 2, because the initial approaches take too much time. Okay. So I will try to explain it better. So what we have here, or what LeetCode wants from us, they want us to find the servers that had handled most number of requests. Okay, we will have servers from 0 to k minus 1. Okay, k minus 1 we will have key servers, and we will also have an arrival of requests and the time that those requests arrives, and not only that, but also how much time it costs to process those requests. Okay, so you have the servers, you have the requests arriving, and you at a specific time, and the time that they take, and they tell specific rules like the requests are 0 indexed. Okay, so you will have arrival array of n requests, and the position of the requests is the eth that is told in here. Okay, so the first position of this array is the 0. Okay, of the is a 0 request. Okay, and it is with that 0 that you do this math here, and this math here is because you for a server, there are 2 ways a server can process a request. Either it maps directly to let me explain again. You have requests that arrive. Okay, if all servers are busy, the requests are dropped. Okay, if and then you have the rules to map to a request to a server. Okay, and the rules are: you get the index position of the request, and you do the mod with k, and this mod will give you the server that will be responsible for processing this request. But if the server is not available, you need to find another one. Okay, you have to find another one that is available, and you have a rule to do that. Okay, and the rule is to try e plus 1. If e plus 1 is not there, you try e plus 2. If the e plus 2 is also not available, you try e plus 3. Okay, and you continue doing this logic, and in the end if you find nothing, you go back to the beginning and try from 0 and then 1 and then 2 until you find the ETH. And if you don't find an available server, the request is dropped. Okay, this is generally it. So let's try to make this description more visual with a test case. Okay, so we have here our test sample. Okay, we have 3 servers that go from 0 to k minus 1, 0, 1, 2. We have the requests, that is the 0 request, the 1 request, the second request, okay, 0 based. And then we have the time, okay, the time at which the request arrives, and we are told that the time is strictly increasing. As you can see here, is always increasing, the time at the request arrives. And also you've got the load, okay, how much a request costs. So let's try to process this and see how it happens, and then it will be easier to explain the solution, and I think you will understand. Okay, because I was very confused with the indexes and stuff, and that took me a lot of time. But well, I understood it, and now I'm going to explain it. So what do we have here? We have the 0 request, right? And the 0 request will be we can do this order. First, find target. Find target with request module k. Okay, so you have here request number 0, mod k, it is 0, right? So we will try the server 0. This is how it works. So we try the server 0, and what time we will do at 1 time, okay, and what cost is 5. So 0, 5, it will be like 1, 2, 3, 4, 5. No, 5 is here. Okay, like 1, 2, 3, 4, 5, exactly. So what this means, this means that the server 0 is occupied until 5. Now next request is 1. 1 module k is 1 because k is 3. So, and we have a request that arrives at position 2 and has a 2 duration. So 2, 1, 2. This is 1. The third request arrives, index 2, 2 module k is 2, 2, and this, it will be assigned to server 2, and it will arrive at position 3, and it will have a duration of 10. So 1, 2, 3, 4, 5, 6, 7, 8, and for the purpose of this exercise, the rest we don't need to represent it. Okay, so 2 is busy. So next, what comes next? 3 is the index number 3. In E3 module k is 3, so there is nothing remaining, so the next element will be 0. The next server will be 0. So 0 at position 4. What we see here is that 0 is occupied at time 4. So what we need to do, we need to check the next servers, okay? And after 0, the next one coming is 1. Is 1 free at 4? And we see that he is free at 4. Okay, it ends up here, so you can start it here. And so we do 4, and it has a duration of 3. 4, 1, 2, 3. Okay, we were lucky. Now we go to, so this is completed, this is completed, this is completed, and this is completed. Now the fifth request, which is for the index 4, we do 4 module 3, which is our k is 3, is 1. So at position 8 we will have duration of 1. So once again here, duration of 1. Done. Now 5 module 3, 2 is occupied. 2 is occupied. So we will, as we get to the end of the servers, we have to go around, like round robin. We have to go around. So we go to 0, and 0 is free, right? Let me just tell you that we know that 2 is busy because of position 9, right? Position 9, 2 is busy. So we go around, and then the next one is 0. And duration is 2. 1, 2. Okay. Then the next one is 6. The index 6. 6 module 3 is 0. 0, the server 0 at time 10. Is it free? It is not free. It is not free. So what we do is check the next one. The next one is 1, and 1 is free. Duration of 2. Okay, so what you can see from this is that 1 is our busiest server, and is the one that we should return. This is the algorithm working in practice, and I just did the algorithm at first, just like I have explained you, and I did all the checks, and I went around and around to seek a candidate, and that's why I had the TLE, time limit exceeded. To pass this question, we need a smarter approach. Okay, and that's what I'm going to explain you next. So the solution was based in 2 data structures. One, a tree set, and another, a priority queue. Okay, and we want these data structures to have some kind of properties that are always true. Okay, what do we want? We want the tree set to always have available servers. Available servers will always be in this data structure, and busy servers will always be in the priority queue. This is what we will try to achieve. Okay, so in each iteration we will need to maintain this property, because sometimes what can happen is that we can have available in priority queue and busy too. And busy. So in these cases we need to move the availables to the tree set in order for us in order to maintain the properties that make our solution work. Okay. So just to further explain, our solution for this case would start with placing 0, 1 and 2 in our tree. Okay, then what would happen is that we assign 0. So when we assign 0, 0 is removed from here and goes for the priority queue. And we not only add 0, but we also add when its end, what is its end, and it is 5. So after 5 we have 0 free. Next we add 1. We go to 1, we remove it from the tree set and we add it in the PQ, and it will finish at 4. So we add 1, 4, and you should know already that priority queues order themselves. So this would be the correct order of the priority queue. Okay, so what's next? Okay, the next step is 2. Okay, 2, and 2 will be removed from the tree set, and we'll go here, and it ends at 12. It ends at 12. And yeah, so we have nothing available here. At the fourth request, so yeah, I'm sorry, this is wrong. This is not 4, this is 3. 1 ends at 3. So then here in the when the fourth request arrives with a start of 0, what we do? Well, our tree set is empty, but what we need to do? We need to remove from the priority queue the elements that are available in order to maintain our data structures properties for this solution. So at the time 4, 1 is already available, so we need to pass 1 to the tree, and that's exactly what we do. So the 1 is removed from the queue, the priority queue, and if we add more entries we would remove them too. So 1 is available. 1 is available, and we assign it this request. Okay, and when we assign the request, we remove it from here again, and we add an updated statement, an updated entry in which we say that it ends at 6. Okay, and then in the next request we go to 8, and when the time is 8, there are some things here that we need to see again, update again, right? Because these 2 requests are available now. So the first thing that we do is to pass them to the tree set. So 0 and 1 are now available. And as this is the 4th index, we do a mod and we get 1. So 1 is available. So we remove it again from the tree set, we put it in the priority queue again, and we add 1. So we add 1 and 8. It ends at 8. Yeah. From here, what is the next is 9. 9 is the next. Do we have something here that needs to be updated? Yes, this one is available. So we pass 1 to here again. And we are at position 5. 5 module 3 is 2, and what we see is that true is still busy. Okay, 2 is still busy, so we need to see if there is something that comes next to. And the way we can do this is by using sailing method in the tree set. This is why the tree set is interesting, because we can seal and ask for elements that are equal or bigger than 2. Okay, and we see that we have nothing. We have nothing better than, nothing greater than 2. So the next step is to see if when we go around we find something. And that's also when the tree set comes handy, because we have the first method. and it will return the first method in here, the first object in here, and it will be 0. Okay, because it is the next available. So the tree set is used to have an ordered registry of servers, and it has the functions like sewing that allows us to get the next element greater than a given input. I'm sorry if this is being too much confusing, but this is pretty much it. We have a tree set with the available thing, with available servers. We have the priority queue with busy servers, and we have to maintain this property throughout our solution, and that's how we solve. Okay, if we didn't use the tree set and we went for an hash map and we had all the entries in here at all times, imagine if there are like 5 servers, we would need to check like, okay, 2 is busy, okay, so let's try 3. Oh, it's busy too. Let's try 4. Oh, it's busy too. Okay, let's try 0. Oh, it's busy. In this case, it wouldn't be busy, but this is the extra work that you do. And if you add 1000, you'd need to do this 1000 times. Okay, and when you go for this solution with the tree set and you organize your solution in a way that the available servers are in the tree set, you never do this. Okay, because you only have available servers in here. This is the key approach to solve this question, at least with an approach like this. So let's go to the code. I'm taking a lot of time, but hope that it's been worthy. Okay, so about the code. This is something, this was created when I was doing the design for this question, but so this is the tree set that I told you with the available servers. This is the priority queue. In the priority queue we'll have an entry for the server ID and an entry with the vast minute before it gets available. And we have an array with the count for each server, okay, because we want the server with maximum requests, and we use this array to count it. And yeah, we start by adding servers to the tree, all the servers, just like I have told you. In here we add all the servers first because they are available at the beginning, and then what we do is to process each request. And the target server is defined by the eth request module with the k. The time is the time at which the request needs to be processed is in the arrival request, and then we need to do that work that will help us maintain the property in which priority queue always only have busy servers, and the tree set only has available servers. Okay, this is fundamental, and that's what we do here. We remove element from the priority queue and add it in the available tree set. What we do next, if we contain our target server, or in other words, if the target server is available, we update the server stats. Okay, and the server stats here is the count. Okay, we update the count. We not only update the count, but we remove from the available tree set. We add, it's updated. We remove, it's updated. We add the server and its updated end in the priority queue because it is busy now, and we also have a variable with the maximum number of requests, because then we will use it to return our answer, and you will understand why very shortly. So if we have our target server, we update the server stats. You know, if it is so it was unavailable, we need to change it to busy. We need to update its number of requests done, and that's it. Then okay, if it's not available, we need to search next if there is any server in order. Okay, if the target is 0, we need to find 1 or 2 or 3, the next one that is available, and for that we do available.ceiling and target. Okay, and this will search for the next element bigger than our target. Okay, and if I'm not mistaken, it will do it in log of n. Okay, in log of n time, and it will do it in log n time because this is a tree set. And if you don't know about the tree set, you can search about it. It's a very cool data structure. So yeah, so update server stats, and you go get the first one which is bigger than this. It could be null, and if it's null, what the return is false. So we need to find an element that is from the back. Okay, so what I mean is that if we are searching for 1 and 1 is busy, we go check 2. If 2 is also busy, so we don't find an available at that has a greater ID, we need to start from the bottom and find some. And that's what I do here by doing available.first. We'll start the search from the beginning. And yeah, in the end, what do? We create our list. We check for all the servers and see their request count, and see if the request count is equals to the maximum request count. If it is, we add it to the answer, and then we return the answer. I took a lot of time explaining this, but it's about it. Okay, we we first add all the servers to the available tree set. We always do this work of maintaining the availability property for the tree set, and the priority queue will always maintain it with busy. And then if we find our target server, we update its stats. If we don't find it, we will check up front if we'll check in front of us if there is any server available. If we don't find it, we will check from the beginning and if we don't find, we drop. Okay, we don't do nothing if we don't find. We just because yeah, we just don't do nothing, don't need to do nothing. And in the end, we go through each server request count and see which one have maximum value. Okay, so that's about it. Okay, that's about it. I hope it was helpful. It was a tough question to do for me, challenging also a bit to explain, but hopefully it was worthy for you. Okay.